Good morning, everyone. Welcome to AWC webinar number 37. My name is Alex Bassini. I'm the Business Development Manager here at AWC Solutions. Today, we are joined by Ian Piro from Anaergia. Good morning, Ian.
Morning.
Excellent. So I don't know if you can hear me okay. I think the volume's a little low on my end. But, Anaergia, I have the hardest time pronouncing that. I know it's a German company, but it almost sounds Latin or Italian. So I'm sure there's a really interesting story behind it. So today we're going to be covering wastewater biogas generation. I know it's a little bit somewhat off topic as to what we've done before with the water treatment industry. However, it does tie into the wastewater. I've always had a soft spot, of course, for the energy sector. I remember 10 plus years ago, I was at Georgia Tech and we did this course on alternatives of alternative energy. And they had all of them, right? Solar and wind and hydro and nuclear, et cetera. But we never really touched biogas in the wastewater industry. And there really is a connection between, water and energy. And it's very direct, right? You need energy to treat water, and then a lot of times you'll need water for the energy side. So I'm pretty excited for this. This is something that is pretty near and dear to my heart after water. So, Ian, AWC Water Solutions has a division that focuses on energy right now. It's called the PTC Group. So welcome to the PTC Group that's logging in as well. And we can get started. So a quick, the webinar series has kind of grown over the years. We actually turned, I think we began in April of last year. So we're just over a year. We're at 37 now. And of course, all of these are all covered. If you've missed any of them or you want to go back to the YouTube channel, Rachel will be putting in the YouTube channel link in there. You can go in there and review some of them. No, there isn't a test at the very end of this, but there is some pretty cool information as you go over the last few months. Quick thing about AWC. So we've been around for 40 years. We design and build water and wastewater treatment plants. We have close to 600 packaged plants worldwide. Mind you, most of them are here in North America, but we continue to grow. Everything gets divided into three. So we do, of course, we've got our standard potable water plants, dissolved air flotation clarifiers. We have wastewater, which is going to tie into today's subject with both MBBRs and MBRs. And then we have skid mounted systems, which kind of tie in to each other. And especially as you go into wastewater, once we look at wastewater reuse, or in this case, wastewater reuse for energy, there's always a way that you can add some of these skid mounts for both UF and RO. So with that, enough about us, wastewater biogas generation. Ian, take it away.
Okay, great. Thank you, Alex. I'm going to go ahead and share my screen, transition things over.
Yes, we can see your screen.
Okay, can everyone see it? All right, make it a full screen. So yeah, thank you, Alex and AWC, for organizing this. It's the YouTube channel is great. It's 36 of them, 37 after this. It's a great resource to be able to have these little bite-sized technology summaries. So glad to be a part of it and glad to contribute. I really wanted an hour to talk, but Alex, kind of like the Rolling Stones, you can't always get what you want. So he gave me 15 minutes. So we got to get cranking. A lot of good stuff to cover. So my favorite thing about the water and wastewater industry is that we tackle some of the largest environmental problems that society faces, that the world faces, like really every day with our everyday jobs, be it front lines at a wastewater plant or a water plant or the engineering side or even project development. So not unlike our industry, Anaergia, our mission is to take the largest organic waste streams of society and provide a series of solutions to be able to convert this waste. We consider waste a feedstock to be able to generate valuable products such as renewable sources of energy, fertilizers, and obviously clean water. So a big piece of this is utilizing our existing wastewater treatment infrastructure to be able to divert organics away from landfills where they would be emitting methane to wastewater treatment infrastructure to be able to generate valuable end products, again, such as energy, fertilizers, and clean water. So if you look over here, this is what your typical kind of waste management process flow looks like for a town. You have your residents and your municipal waste goes to landfill or the incinerator, and then your wastewater goes to a wastewater treatment plant, where your sludge may or may not get land applied as Class B or go to a landfill in a lot of cases. So just energy is kind of vision for the world, and what our technologies are all centered around doing is bridging the gap between municipal solid waste and wastewater treatment infrastructure, because you can revitalize and retrofit our existing wastewater treatment infrastructure to be able to divert materials away from landfills create feedstocks for anaerobic digestion, and then again generate renewable energy sources such as renewable natural gas, which is methane in kind of our current carbon biogenic cycle. It's kind of offsetting the need for new fossil fuels, and then different types of fertilizers. So to kind of zoom even further about what the process actually looks like at a wastewater plant, process of anaerobic digestion, it really is, and I guess Alex gave a good intro to this. It's just the center of where waste management, organics management, and water all meet with energy. So by utilizing anaerobic digestion at wastewater plants or standalone merchant facilities, you're able to take the predominant waste streams of society, municipal garbage, where you can extract the organic fraction, convert to a feedstock and send it to an anaerobic digester, or your just general residual sludges you generate at wastewater treatment plants. And through processing it through an anaerobic digester, you're able to produce biogas that you can either power engines for renewable electricity, or as we're seeing increasing trends towards making pipeline quality renewable natural gas. And then you also generate a digestate, which can be dried and pyrolyzed to be able to produce an urban fertilizer free of contaminants, thus returning nutrients back to the soil, kind of closing the loop on the waste management cycle. So just to kind of zoom even further into the capabilities of anaerobic digestion. So it can take a anaerobic digester can take a wide range of organic feedstocks, everything from energy crops. You see more energy crops kind of in Europe and some in Canada than the US, but I think we're catching up. These are purpose-grown crops like grass or maize that are just grown for feedstock to anaerobic digestion. You can also take agriculture residuals such as manure. We're seeing a large uptake in dairy manure digester projects because the carbon intensity score is very favorable. So the gas that a dairy manure digester creates is a very, very valuable gas for its environmental attributes that you can sell in different types of state and federal markets. Food processing, of course, it's everything from fog, fats, oils, and greases that you would collect from a grease trap, from a restaurant like a fast food joint, or your larger food processing facilities, and then of course wastewater treatment sludges. And you're able to take this material again and produce valuable end products such as renewable natural gas and recover nutrients for fertilizers. So to kind of go even further down, just taking it one step at a time to kind of get more to a granular level, what is anaerobic digestion? It's the natural biological conversion of organic materials like those feedstocks that we talked about on the previous slide into methane and carbon dioxide gases. Like biogas is predominantly methane, about 60% on average, but with the balance being carbon dioxide and then some trace other gases such as VOCs, siloxanes, and H2S. And you're also producing a nutrient-rich fertilizer, which can be land applied or it can be further processed through drying or pyrolysis to be able to create a soil amendment that you can use, as an urban compost or other types of applications. So there's several different types of digesters, but for the case of this conversation, we're going to focus on continually mixed digesters. There's plug flow, there's batch garage digesters, there's lagoon digesters, and there's other like high rate, more industrial digesters too. But for this, at Anaergia, we really specialize in these continually mixed systems. So at a very high kind of process level, you have your input, again, those feedstocks that we talked about, say your municipal sludges or different types of food waste, is pumped into the digester and mixed with the digestate, which is your essentially like your biomass. Those are your microorganisms. It's a complex colony of microorganisms that biodegrade the waste into biogas and also the digestate. And at the same time, you want to heat the biogas reactor to, you kind of think of a digester kind of like your stomach. The microbes in the digester like to be around 90 degrees Fahrenheit. And then, of course, you generate your biogas, which accumulates in either the headspace of the tank, in case you can put a membrane gas holder cover on top. It looks kind of like a balloon. I'll show a picture of it. Or you can pipe the gas over to separate storage. So talk a bit about the actual biological process. So it happens in 4 key stages. The first stage is you have your hydrolytic bacteria who take your larger molecules, your carbohydrates, your fats, and your proteins, and break them down into more soluble components that then the other microorganisms, the acetogenic bacteria, can then take those more soluble molecules into their membranes and then produce volatile fatty acids, which then in turn can be utilized by methanogens, which is a kind of archaea, to be able to produce biogas. So really, like a long story short, it's a complex colony of microorganisms that all work together in concert, not unlike activated sludge, to produce biogas. And really for here, your two limiting factors are really the hydrolysis step, trying to reduce the molecules down to the smallest. And you'll see in some cases, digesters will actually employ a pre-treatment step where they will either chemically or physically try to break these molecules prior to entering into the digester. That's you can see this with like thermal hydrolysis or chemical hydrolysis. And then your methanogens too are very, very finicky microorganisms. So they tend to also be kind of a rate limiting step, and they're very sensitive to the conditions within the digester. You see two predominant types of digesters from a temperature standpoint. Your mesophilic, which we mainly operate in. Again, this is, think about your body temperature. Your bugs like to be, in the 90 degrees Fahrenheit, very, very similar to our own biology. But you can also run them at higher temperatures for thermophilic, and there's different types of process advantages too, especially around pathogen reduction. So moving on, talk a bit about the biogas. You can see a wide range of methane in the biogas. We typically see anywhere from 40 to 50% methane, and the balance being carbon dioxide, then other trace gases such as siloxanes and hydrogen sulfide. These trace contaminants tend to cause issues with the reuse of the gas. Like for instance, siloxanes, if you don't remove them prior to putting them into an engine to generate electricity, you're going to oxidize silicon and end up with this white powder, essentially sand, on all of your downstream equipment. So it's important to be able to put processes in place to be able to clean up the gas, to be able to beneficially reuse it. So it kind of brings us to the energy recovery options. We typically see two predominant options beyond just flaring or making heat in boilers. And it's renewable power through the combined heat and power engines. And for this, again, you have to condition the gas prior to burning it in the engine to remove H2S, ammonia, siloxanes, and VOCs, because they can be pretty hard on equipment. And we're seeing a huge shift kind of away from CHP towards the production of renewable natural gas. This is pipeline quality gas, where you kind of take it a step further. You still have the same conditioning steps, or very, very similar conditioning steps as you would have to condition gas to go to the CHP engines, but you take it a step further by what we call biogas upgrading, where you remove CO2 to upgrade the BTU value of the gas, and then you're able to either compress it and use it as vehicle fuel, or you can even put it in the local gas pipeline and sell it in the natural gas market. So it's a tremendous opportunity to be able to further utilize biogas and fuel that's generated, again, in our current carbon cycle without having to go to fossil fuels. And it works great for the large transportation sector, and also for harder to decarbonize sectors that aren't necessarily going to be able to go towards solar power anytime soon because of the heat demands such as steel. So let's take a look at what a couple some digesters that we've recently built. So this is Anaergia's Rialto bioenergy facility. But you can see at this facility, the gas is stored in the headspace of the tank and then pumped over to be converted into renewable natural gas. So this particular facility generates just under 1 million MMBTU per year, which just to put perspective, that's essentially the equivalent of taking 50,000 cars off the road with the amount of carbon that it offsets. So just a tremendous environmental benefit, and it's putting that gas right now into the Southern California natural gas pipeline. So those green molecules are moving through the natural gas pipeline because of this Rialto bioenergy facility, and it takes 700 tons a day of food waste, which is extracted from municipal garbage. So it's materials diverted away from landfills. It would end up in a landfill, but now is being digested and producing renewable natural gas.
So excuse me, Ian. I'm just getting a note here that they can't see your screen. Can everybody see a screen?
Oh, you can't see my screen?
Yeah. Okay, that's a yes. All right. Carry on. Go ahead.
Can you see my screen, Alex? Am I coming in clear there?
Yeah, I can see it.
Okay. Moving along. And I'd be happy if anyone wants to reach out, I can send them a copy of these slides too if there's any technical problems. But so another example of a digester design, this one does not have the floating membrane covers. These are fixed steel covers where the gas is piped over to this storage sphere. And then the gas is utilized in these combined heat and power engines to produce 3.8 megawatts of power. This is located in at the Camden County Municipal Utility Authority in New Jersey. It's an 80 MGD wastewater plant. And it is able to power the critical loads of the facility all off of biogas. And they put the system into place after Hurricane Sandy because they want the ability to have complete resiliency in case they lose access to the power grid. So this plant is able to go into island mode and, again, purely power the critical loads of the facility from both biogas, and they also have a solar array on their primary clarifier. So it's a great example about how a wastewater plant can, by utilizing its own biogas it is generating, by digesting its internal waste activated and primary sludge, to be able to produce biogas to power the facility. So for the wastewater folks in the virtual room, I want to throw up a couple of just general process parameters here. So when you look at like digesters, so your SRT and HRT is the mean residence time that it takes liquid to go through the digester. Now, the thing I really want everyone to focus on here is that your typical conventional municipal digester is being fed 3 to 6% solids, depending on if you're thickening your sludges. But, so pretty low solids content going into the digester. The digester itself is only operating at about 2 to 3% solids. So the balance of that is all water. So as a result, the organic loading is about 100 pounds per day per 1,000 cubic feet. So in line with those numbers, there's a huge opportunity for digesters to be operated more efficiently and kind of follow the industry trends towards process intensification. You look at some of the systems that AWC is developing with like MBRs and package plants. These days, you can do more with less space with more process intensive technologies like MBRs, or Pfas media and aeration basins. So it's about time for the digesters to kind of catch up and operate more efficiently with smaller footprints. So the technology that Anaergia has developed and deployed, we have several installations in North America, is our omnivore digester platform, where we're able to triple the capacity of existing digesters, or if it's a new construction digester, it's a third of the footprint, by applying two key changes or optimizations to kind of the proven digestion process that's been around forever. We introduce a specialized thickener, so we're feeding the digester at over 12% solids. So again, that other digester is being fed at 6. The omnivore is getting fed at 12%. So you're getting, again, less water into the digester, and the digester is operating at around 6% solids. So what that means is that you're able to triple the capacity of the digester. So if you look at the organic loading rate, the conventional digester that was operating at 2 to 3% solids was, the organic loading rate was, around 100 pounds. You can see with the omnivore, which is now operating, it will say around 6% solids. That seems to be the common operating. You're at 300 pounds. So you're able to immediately unlock additional capacity by either retrofitting this to run at higher solids, or again, if you build a new tank, it's third of the footprint. So I know you might think to yourself, why isn't every digester doing this? Like why do we operate our digesters at municipal treatment plants at such low solids? Well, the issue has been historically mixing. So mixing is kind of the heart of the digestion process, because it allows your inbound feedstock to maximize contact time with your biomass, to be able to degrade the solids and the volatile solids and produce biogas. And your traditional mixing systems can't keep up at 6% total solids. So you have like your linear motion mixer, which is a kind of a plunger style mixer that goes up and down the tank and disperses the liquid kind of like this. And then you have your pump mix system, which pumps and recirculates the sludge in the tank at various points. They do a pretty good job up to, maybe 3 or 4 to 5% solids. But once you kind of get over 5% solids, these mixing systems really can't keep up. So that's why Anaergia has developed our PSM, our permanent synchronous magnet motor mixer, which uses a high torque electric motor. It's the same motor that a Tesla uses. Very, very efficient, high torque, and it's able to mix the tank. These are CFD models, and really the takeaway thing with these figures that the darker the colors, the less mixing, less velocity in the tank. So you can see here that at 6% solids, traditional mixing systems just couldn't keep up. But with Anaergia's mixing system, we are able to unlock that capacity by completely mixing a tank, getting over 90% of the tank to a critical velocity well over 0.3 feet per second, which we find is just the optimal mixing set point. So kind of in summary, with by converting the traditional digesters and optimizing them for high solids, you're able to triple the capacity, or you can gradually increase capacity over time. You can first upgrade the mixing systems, and then over time increase the thickness of the material, the percent solids going into the digester. Less capital, this means smaller tanks. You can consolidate tanks. You can work with existing sludge holding tanks, convert them over to digesters. And then you're able to kind of transition wastewater plants from net energy users to net energy producers, because by increasing digester capacity, you can bring in more outside waste, outside feedstocks, produce more biogas, and ultimately become a net zero or an energy exporter. So just to kind of round everything out, this is a project that we did in Victor Valley, California. Here's an omnivore digester. This little digester right here has the same capacity and throughput as this larger digester, all by running at the higher percent solids with the advanced mixing system and then with the screw thickeners that we use. So with that, I am going to catch my breath and I guess turn it back over to you, Alex, and we can start having a conversation. I welcome any questions.
Excellent. Thank you, Ian. Wow, that was very compact. And I have a long list of questions myself, but I'm going to open it up because I know I have a few of them here in the chat box. Andrew, thank you very much for your questions. I can always count on those. So the first one I have here is where to go. Oh, the chat box is there. All right. So it says, could you talk about the residuals that would come out of the final digester? That was actually one of my questions as well. What's the digest state look like?
Yeah, so it looks like it's essentially a sludge. So it'll be in the case of the omnivore digesters, it'll be a 6% solid sludge. So that material will then be dewatered to about, either through a belt filter press or a screw press or, like a centrifuge to about 25% solids. And it looks like kind of a wet mud. And then that's when it can either be land applied, or you can take that kind of wet mud and you can further dry it into pellets, and then it essentially looks like a mulch. And you can market that as a product. It really depends on what the what your end use for the digestate is. If you have a relationship with the farmer and you can land apply it, then you don't necessarily have to dewater as much, or you can put it through a dryer and make pellets. It just depends on the end use of the material, but it's versatile.
Okay. You mentioned something about the mixing and how important mixing is. So you're saying that just by making sure that you've got proper mixing going through the digester, you could increase the capacity, or potentially not just increase the capacity, but lower the amount of time that it takes to go through the process. Is that right?
Yeah, it still takes about the same time to go through the process. You're just able to put more material through. So you still want to keep that solids retention time, anywhere from 15 to 30 days. That's pretty standard for wastewater to be able to meet the Class B standards. But you're able to put more material in though, and still meet that same SRT.
Right. Okay. I have another question here. It says, what type of thickener is Anaergia recommending for thickening? And is there any thickening primary and secondary? Oh, it just moved on me. Primary and secondary sludges simultaneously.
Yeah. So that is an excellent question. We prefer screw thickeners. And we actually manufacture our own, because that's a very important part of the process, because to be able to take your both primary and waste activated sludge simultaneously, from that, 3 to 6% solids up to 10, it's a very kind of sweet spot piece of equipment, because your gravity belt thickeners or like rotary drum thickeners aren't really going to take you up to that point. So we find that screw thickeners are right in that sweet spot of taking that, 3 to 5 or whatever percent solid sludge and bring it up. But also if you can't thicken both your waste activated and primary sludge at once, we can also do recuperative thickening, where we pump off a portion of the digestate in the digester, we thicken it to the 10% solids and return it back to the tank as well. So that's easy for a retrofit, so you don't have to redo all of your sludge piping into a screw thickener, and you also get a much more homogeneous material to be thickened.
Okay. I hadn't noticed that the top part of it was a membrane. So that is essentially a membrane cover that you're putting on it?
Yeah.
Okay, and so how full is the tank, I guess? So what's the active volume within a tank? Is it, out to the tippy top, or are you operating at 30, 40%? What does it look like?
It's pretty close to the top. I mean, it depends on the tank design, but you definitely want a little bit of headspace for the gas, but you want to optimize the working volume of the tank, so and again, that goes back to what your solids retention time is and everything else, but it varies on tank design, but you really do want to have as much active volume in the tank to kind of maximize the tankage.
Right. Okay, I have another question here. Does this produce Class A biosolids? And what is the concern with Pfas?
Okay, so Pfas is a great question. And so a standard digester produces Class B sludge, which can be land apply, with like limited human exposure, but if you want to do Class A, then you have to dry, or I guess you could do like a THP process. And then for the PFAS, even your Class A sludge right now is still going to have PFAS in it. It's not going to, there's no PFAS standard yet. So that's why we have a pyrolysis technology that we use, where after the sludge is dried to about 85 to 90% solids, then we put it through pyrolysis, make a biochar, and from there you're completely removing all PFAS, bisphenol A, all emerging pharmaceuticals, all the compounds are being removed through the pyrolysis reactor.
Okay, excellent. So I've got another list of questions myself, and there's more coming in, but what we're going to do is we're going to wrap up and we're going to have what I call an after party. If anybody wants to stick around and have more questions, we're always trying to make sure we keep this as compact as possible. And right now we're hitting the 26-minute mark. So again, thank you very much for coming. There is your contact information there. If anybody has more follow-up questions that we don't answer on the second portion of this, please make sure you can reach out to Ian and send him an email. On the webinar front, we do have some upcoming webinars. We're going to be doing some ceramic membranes and wastewater. Thank you, Joe, for putting that together. Some electrocoagulation we're going to be covering, along with some water risk assessment. So it goes outside of just water treatment and technologies, but more of water risk, which is something that's coming up. Again, shameful plug, if anybody has missed any of the YouTube channels, please make sure the link is in the chat box. Have a look at it, subscribe, and there's more of these that are coming out. There's more. This is just webinar number 35. There is more of them that are coming out with that every single week, or every 2 weeks rather. So with that, thank you very much, everybody, for tuning in. We can wrap up right now, and I will see you again in 2 weeks. Goodbye.